Today we're looking at 3D masks in Python and how we can create an STL file from these masks. An STL file is a 3D file that you can view in a 3D viewer on your computer, for example, or you could send it to a 3D printer and you can actually print a physical copy of the mask. The reason I'm interested in this is because it actually recently came up in my research. We had 3D tumor masks from physicians that they got by looking at PET and CT scans. So we knew what the tumor looked like in space. And what we wanted to do is we wanted to take these 3D masks and print them using a 3D printer. It turns out that taking one of these 3D masks in Python and turning it into an STL file that you can print isn't as easy as you might think. Today we're going to look at two important packages for taking these 3D masks and turning them into 3D printable files. The first is the marching cubes algorithm from scikit-image. Now it turns out that 3D files on a computer are specified by the surface. And what the marching cubes algorithm does is it takes a 3D mask and it finds all the points on the surface. And not only that, but it finds the corresponding ways that you draw triangles between those points to actually show off a 3D object. Once we have all these points, we'll use the numpy-stl library to save them in an STL file, which we can then open on a 3D viewer on our computer, for example, or send to a 3D printer and actually get a physical copy of the 3D mask. Be sure to like and subscribe as always, join the Discord server, there's a link below, and enjoy. So the packages you actually need to do this are very basic. I have NumPy, which is standard in most Python applications. Matplotlib is just for me to do a little bit of visualization here. Scikit-image is going to be used to create the faces and vertices of the 3D mesh we're going to create. I'll get into that a bit later. And the STL mesh, that's going to be used to export the file so we can actually view that 3D file on our computer and even send it to a 3D printer to print out. So remember, the whole goal of this video is you have a 3D mask. That means everywhere in space it's either a 0 or a 1. And you can form sort of blobs like asteroids. In the case of my research, I was looking at tumors, but you can create masks of basically anything. And I'll show you one right here. I'm going to create a mask as follows. The mask is going to be in 3 dimensions, and it's going to be specified by z is less than x squared plus y squared is less than 1.5z. And you might think, well, what the heck is that? Well, suppose I'm at a certain height, a certain value of z. Maybe z is equal to 3. And then I also have my xy plane. It says that 3 is less than x squared plus y squared is less than 4.5, I guess, if z is equal to 3. So there's a region there where it's true, and those are going to be voxels in space equal to 1. And then it does that for all values of z, and as z gets bigger and bigger, that ring sort of expands and gets larger and larger. And this is sort of a parabola-like object. So the way I create this is I'll create x, y, and z arrays as follows. So x and y will go from -1 to 1 in sort of the xy plane. Z is going to go from 0 to 0.5 in 100 steps. And what I do when I'm generating masks and I'm thinking about 2 dimensions and 3 dimensions, remember I can take 2D cross-sectional slices that I'll actually plot. I'll make a 2D and a 3D mesh grid. So I create a 2D mesh grid really easily. You just take in these one-dimensional arrays that you create here, and you specify them x2d, y2d. I use the indexing equals xy. It default is ij indexing when you use Meshgrid. This just keeps x, y, and z in order, and it's really basic and simple for things like plotting. Then I also do the same thing with the 3D Meshgrid, only this time I'm feeding in x, y, and z. And the reason I'm creating both a 3D and a 2D is because I'm going to use the 2D Meshgrid to do a little bit of plotting of the cross sections of the mask we create. So I'll import my packages and I'll run this cell. And of course, like I said, x, y, and z are all 1D arrays. If you're confused what's going on here, I highly suggest you check out my Meshgrid video. I'll put a link above and also in the description as well. So once I have my mesh grids here, it's actually really easy to make the mask. I just have x squared plus y squared is greater than z times x squared plus y squared is less than 1.5z. Of course, each of these arrays here is a corresponding mask. If I look at this, it's just an array of trues and falses. I can set this equal to its own mask. And if I look at m, it's just an array like this, what I just had. And I can take, for example, let's take the 50th point in z. So my z goes like this. So of course, this is the x axis, y, and then z axis. I'll take the 50th point, which corresponds to z equals 0.25. So I can look at this, and this is a corresponding 2D slice. And I can plot what this looks like. I'll go plot.pcolormesh, and I'll use my 2D things now because I'm taking a slice. So this is where the 2D mesh grids come in handy. And I can plot this given mask, and it sort of looks like this. And I'll make the figure a square. Fig size is equal to 5 by 5. And now you can see that whenever x squared plus y squared is greater than 0.25, which is the radius, the value is true. And of course, I can then, because it's trues and falses, the rules of Boolean logic, I can multiply it by this. So that says when this is true and this is true. So x squared plus y squared is greater than z, and x squared plus y squared is less than 1.5z. And I modify my mask, and I get sort of a ring that looks like this. And that's sort of what I do below here. I have my mask, and I can plot, for example, here's the 8th slice. But of course, what I was just looking at was the 50th slice. This is where z is equal to 0.25. And I can look at different slices. So for example, if I go down to 40, I have a ring that looks like this. If I go down to 20, I have a ring that looks like this. And the ring is sort of moving up. And you can imagine that we have a three-dimensional object with a finite wall thickness almost. And it's a parabola, right? Because it's x squared plus y squared. And you have a sort of a thick parabola. And what we want to do is we want to create a 3D file from that parabola and save it in a format that we could eventually 3D print. So for this, we need the vertices and the faces of the surface of this object. And you might not know what that means. What is a vertex and what is a face in this context? I have a diagram down here that sort of specifies that. So you could imagine that an object, a 3D object, is just a bunch of triangles all pasted together. And like you could think of a video game, for example. If you want to show a 3D object, you just show all these triangles from a certain angle. And that sort of creates it's sort of like a hollow object because these triangles are only on the outside, but it doesn't matter because the object doesn't need to be truly three-dimensional. You just need to see the surface to get the context of what the 3D object is. So the faces correspond to a list of 3 indices. So for example, here I have points 1, 2, 3, and 4, and those specify a given triangle. That's what you could think of a face as. A face is just an index. It's a number. It's an integer. It's the first face or the second face or the third face. And if I give you 3 faces here, 1, 2, 3, you can draw a triangle between them, show that in space, and you're all good. The vertices are the actual vectors corresponding to the indices. So for example, indices 1, 2, and 3, faces 1, 2, and 3, they correspond to the vertices R1, R2, and R3. So in order to specify one of these triangles, you need 3 vectors, or 9 numbers, because each of these vectors has 3 numbers itself. So then you can get a single triangle from 3 vectors or 9 numbers. And you build that up over the case of many triangles, and you can make an eventual 3D surface out of these triangles. So how do we actually get the vertices and the faces of this 3D object here? Well, there's a beautiful algorithm known as the marching cubes algorithm. It's implemented in scikit-image here from the measure library. All you do is you feed it in this mask here, and it will find all the points, all these given points here with the triangles on the surface. So by the surface of this, you actually mean the inside surface here, and then also the outside surface. It's just going to take a connected volume. So you can think of this as going up. It's like a finite wall thickness. And it will find all these points on the surface here and all the points on the outer surface here, and it will construct those into a 3D volume. There's also the normals and the values. You can ignore them. They're not important for the 3D printing here. The normal is like the vector that sticks normally outward from the triangle. And I don't know what values is here. But anyways, once you have this, you have everything that you need. And so like I said, the vertices are a list of points that exist on the object. So the vertices are like R1, R2, and R3, and they give the coordinates of each one of these faces, like 1, 2, 3 here. So if I look at the vertices that I have here, this gives the X, Y, and Z coordinates. So for example, this might correspond to this point 1 here. This might correspond to point 2 here, this point 3, and et cetera, et cetera. So you have all these different vectors sort of pointing in space to all the different points on the surface of this 3D volume. So you have all these points, but you really need the faces to tell you where are the triangles drawn between. For example, in this case, the triangle is drawn between 1, 2, and 3, and also 2, 3, and 4. But there's not a triangle drawn between 1, 3, and 4, right? So the faces tell you of all the points that I'm given here, which points am I drawing triangles between? And that's, you can see here what the faces are. So it says, I need you to draw a triangle between point 2, point 1, and point 0. So there's going to be a triangle drawn between these 3 points. Also point 0, point 1, and point 3. So that's like this point, and then whatever point comes after here. And then it goes all the way to like 50,000 points because there's a lot of points on the surface of this object. And so you can see that with the list of the vertices and then the list of the faces, which tell you which vertices to draw triangles between, you have all the information about the surface of this 3D object. So we have the ingredients to save this as a 3D file, which we can eventually 3D print or view in a 3D viewer, such as the one I'll show you later in this video. So to actually create the 3D object, we'll be using numpy-stl. I imported the stl library at the beginning of this video. And it uses the list of the vertices and the faces. So the first thing we do is we create an object 3D, which you can see down here. And it's going to contain the same number of elements as there are faces. Remember that a face corresponds to a triangle. It's like the list of 3 indices. So each face is one triangle. So this mesh is the same like length as the number of triangles that there is. And what we're really interested in filling when you're dealing with meshes in this library is the object3d.vectors attribute of this object. So each element of object3d.vectors, so there'll be however many faces there are. I have 100,000 faces. So there's going to be 100,000 faces. Each one of those faces has 3 vectors that I need to draw the triangle. And so what we're going to do is for each element in object3d.vectors, we're going to fill in those 3 vectors. And that's sort of how the mesh is saved here. So the first thing I'm going to do is I'm going to define it all as zeros. And it's the same shape as faces.shape0. So if I look at faces.shape, it's this by 3. So this is the number of triangles there are. Each triangle corresponds to 3 points. So I'm going to make it just zeros, which is the length of the face, and it's going to be a data type of mesh.mesh. So I can actually look at the shape of the vectors now. So this is what it's automatically will create it as, and this looks like a complicated shaped array. And if I look at the shape, it's however many faces there are, so that's the number of triangles, times 3 points, so 3 points on each triangle, and each of those points is given by 3 coordinates, and that's why I have this 3 here as well. So with this array here, I have all the information I need to draw all the triangles on my 3D surface. Remember that we initiated them all as zeros. If I just look at this array, everything is a 0. So for example, these 3 points here correspond to 3 vectors. This could be like R1, R2, and R3. And we're going to manually fill them because we've created a mask manually. Now we need to manually fill it in a for loop, and it's very easy to do. So I'll just leave the shape here so you can remember exactly what we're doing. The shape looks like it has no vectors.shape. It's this many faces times this many points per triangle times 3 coordinates per point in space. And so what we'll do is we'll loop through all the faces. So I'm going to list through my faces array. Remember, my faces looks like this. It's 3 indices of the 3 vectors that correspond to one of the triangles on the surface of my object. So again, if I look at the shape of this, it's however many faces, however many triangles there are, times the 3 points. But in this case, the points are given as integer things. So they're given as like 1, 2, 3, 4, as opposed to here in the mesh, I have my 3 points, and instead of specifying each of those points as an integer, I specify it given the x, y, z coordinates. So this is a different way of specifying all that information. So I'm going to loop through my faces. I'm going to take each element in face. So remember, each element of face is a 3 vector that contains integers. So that's like the first 3 coordinates, the second 3, the third 3 coordinates. These are just indices of the vertices that I'm drawing between. And so I loop through the faces. So f is going to be 3 indexes, and I is going to be like 0, 1, 2, 3, 4. And the ith vector in object3d.vectors, so if I look at object3d.vectors, and for example, I can take the first element, and this is going to have 3 vectors that correspond to where I need to draw my triangle between. So this object3d.vectors I, so these 3 vectors, 1, 2, 3, is equal to vertices. So remember, my vertices array looks like this, right? It's just a list of coordinates, x, y, z, x, y, z, x, y, z. And if I feed this, my faces, so for example, these are my 3 indices of my face. If I take index 7 of this array, index 5 of this array, and index 4 of this array, this will give me three vectors. So see what happens when I do this. I take these three indices, and I'm going to grab the corresponding vertices, and it gives me three vectors, this vector, and this vector. And it says to draw a triangle between those three vectors, for example, R1, R2, and R3 in this case. And so what I do is I loop through all my faces like this, and the ith object 3D.vectors. So for example, remember that each vectors in object 3D.vectors is going to be three vectors. So it says my 0th element, for example, take I is equal to 0. So vertices of faces 0, it gives me three vectors here. It says to set this here, these three vectors, equal to these three vectors. So that's what I do here. I take my first triplet of vectors in object 3D.vectors. So for example, R1, R2, R3. And I set it equal to the corresponding vertices of that face. So it gives me this, this, and this. I would think about that carefully and slowly if I were you, and sort of go through the code yourself. So this for loop will set all those three vectors. And now when I look at object 3D.vectors like this, I take the 0th element. Now it tells me the R1, R2, and R3 to draw between. And I get one triangle. And then it gives me R1, R2, and R3 to draw between, which is another triangle, and so on and so forth. And now that I have this object 3D object in numpy-stl, I can easily save it to a file. So I'll save it to 3dfile.stl right here. So here's the 3D object opened in the Windows 3D viewer. There's a little glitch at the top and the bottom, and I'll show you how to fix that. And there's a reason why it occurred, but it'll become self-explanatory very soon. But you can see that all the triangles have been drawn on this object so that it looks like a true 3D object. And if I were to print this in a 3D printer, what it would do is whenever it's like inside this object, for example, suppose there was a top level here, so it was closed off, it would print a solid 3D sort of parabola object like this is. So I'll show you how to fix that glitch so that the top is filled and the bottom is filled. If you look here at my mask, you can see that obviously there's going to be, it's true inside this ring. And if I go to the last slice in Z, which corresponds to the top of the ring, you can see that it's sort of still like that. And so the marching cubes, there's no Z boundary above this object. And if I want the marching cubes to find the edge of the object in Z, I need to actually set this final Z slice equal to 0. And the same thing at the bottom, so that it knows that, there's, empty Z points above this thing here. So it knows that, for example, this layer is the top. So what I can do is, after creating my mask, I'll just set this equal to 0. And I'll do the same thing for my bottom slice as well. And now, of course, it's empty, but the second last slice is like this. And so it knows when it's doing the marching cubes algorithm, it says, well, there's a slice above it that's empty. So these points here must be the top of the 3D object. And now when I reopen it in the viewer, you can see that there's sort of a top layer here. It's now solid on the top. There's not that glitching sort of two-wall feature of it, because it knows that these points at the top here correspond to the top of the parabola object. And of course, at the bottom, it's still going to be a slight ring, just because I have discrete points. And remember that the bottom slice corresponded to 0. So it's going to be a little hollow here. There are ways that you could fix that as well, of course. But here I have my full sort of 3D parabola object. This STL object is something I could send to a 3D printer, for example, to get it printed out. So an important thing I forgot to mention, we created coordinates here, x, y, and z, where x and y go from -1 to 1, and z goes from 0 to 0.5. And we use that to create a mask. And we use the mask to create a 3D object, but suppose that these were the dimensions that you actually wanted the 3D object to be. You wanted it to go from -1 to 1 centimeters, for example, and 0 to 0.5 centimeters. So the actual scale of the object in X, Y, and Z. Well, you'll know when we run this and we get the vertices, which are the vectors pointing to all the points on the edge of this object. This doesn't give it in X, Y, Z coordinates, actually. It gives it in the voxel number. So all of these numbers go from 0 to 100, and the reason for that is because we created 100 points in X and Y and 100 points in Z. But maybe we want them between -1 and 1 and 0 and 0.5. Well, for that, We just need to scale this by the corresponding differences in x, y, and z. So to do that, I can get dx, dy, and dz as the differences between the arrays. Of course, if I take np.diff x here, right, that gives me like the spacing in x. And if I take the 0th element, I get, this, which is the spacing in x in, choose whatever unit you want, centimeters, for example. I do the same thing for y and z. You'll note they'll all have different spacing if I run this. And dr is just a vector of dx, dy, dz. So that's like the spacing here. And dr just looks like this. So the spacing in x and y is like this. The spacing in z is much smaller. And if I want to scale the vertices so that they correspond to x, y, and z coordinates, I need to multiply each one of these three vectors here by the corresponding value of dr. And I can do that by setting vertices equals vertices times dr. And if I do this and I run this cell, my vertices now looks like this. So they're scaled between 0 and 1 and 0 and 0.5 for z. So I run through the rest of the code and I can save this 3D file like I did. And opening it, you can see that my object now has the same dimensions as the mesh grids I created earlier in the video. So now you can see, for example, that the diameter is 4 times the height. Remember, the radius is equal to 1, so the diameter is equal to 2, and z goes from 0 to 0.5. So we have an object that's scaled properly according to our mesh grid. I hope you enjoyed this video. If you did, please be sure to like and subscribe. Join the Discord server as well, and I'll see you next time.